In this video, we'll solve the Airy's equation, y double prime minus xy equals 0. And we'll do this by a series solution. So to solve an equation by the series solution, we make the ansatz try y of x equals sum from n equals 0 to infinity of a sub n times x to the n. So this is a standard power series. We substitute in, so we get the second derivative. The second derivative becomes the sum from n equals 2 to infinity, a sub n, and the first derivative brings down an n. The second derivative brings down an n minus 1 times x to the n minus 2, so that would be the second derivative, minus x times y, so minus the sum from n equals 0 to infinity, a sub n, x to the n plus 1, and that's x times y, and that's equal to 0. Okay, now to proceed to find the series solution, we need to write these two power series as a single power series. And to do that, we need to match these powers of x. So this is x to the n minus 2. This is x to the n plus 1. So we can match it at different values of exponent here. I think maybe the simplest way is just to pull this exponent n minus 2 up to n plus 1, and so to match x to the n plus 1. So we need to shift the index down here. So shift this index to pull this one up to n plus 1. So to do that, we have to write this we have to increase this one by 3 so that this piece here will be x to the n plus 1. So when n equals 2 here, this is 0. So we want this to be 0 at the lower one here. So this would start from n equals minus 1 and still go to infinity. And then to match these ones, this must be a, and then this should be a sub 2. So this one has to be shifted up by 3. So it will be n plus 3 times n plus 3 times n plus 2. Okay? So these two summations are exactly the same. All we've done is shift the index here. And then we have the last one, which we don't do anything to. Okay. So now we're in a position of combining these two power series. The one complication we have is that this starts at n equals minus 1, and this starts at n equals 0. So this one has a x to the 0, a constant term, but this one starts with x. So we can pull out the n equals minus 1 term. That's that becomes a sub 2. And n equals minus 1 will be 2 times 1, so 2a sub 2, so times 2, right? And then we have the summation from n equals 0 to infinity, and we can combine these coefficients. So we have a n plus 3 times n plus 2 times a sub n plus 3 minus an a sub n, and that multiplies x to the n plus 1, and then this whole sum is 0. So this now is written as a single power series. This is the constant term, x to the 0, written separately. And then we have x to the 1 is the first term in this series, and then x squared and x cubed and so on. So now the key step is that if we have a power series equal to 0, then all of the coefficients have to be 0. So this coefficient has to be 0. So that means a sub 2 has to be 0. And then this coefficient has to be 0. But we can solve this coefficient for a sub n plus 3. So that gives us a sub n plus 3 equals a sub n divided by n plus 3 times n plus 2. Right? And that one is only valid for n equals 0, 1, 2, etc. Okay, that's called the recursion relation. So now we have these two equations, a2 equals 0 and the recursion relation. We want to determine all of the a's. Typically there will be two free a's that we cannot determine. So let's see, how does this recursion relation work? The way this recursion relation works is that if we start with a0, right? We start with a0, then when we plug a0 in, we will get a3. Then we plug n equals 3 in, we'll get a6, and then a9, etc. Okay, this is 9. That's starting with a0. If we start with a1 instead, then this equation will give us an a4. And then we plug in n equals 4, we'll get an a7. We plug in 7, we'll get an a10, etc. And finally, starting with a2, here, we'll get an a5, right? But a2 equals 0. a2 equals 0. So starting with a2 equals 0, we'll get a5 equals 0, right? And putting in a5 equal, which is 0 here, we'll get a8, which also is 0. And then the a11 is 0. So all of these a coefficients will be identically 0. Okay, all of these are 0. Okay, so we just now have two coefficients that can't be solved for, a0 and a1. But we can find a3, a6, a9, a4, a7, a10 in terms of the first sequence in terms of a0, the second sequence in terms of a1. So we can find, say, let's say the first 4 coefficients. So if we start with a0, then we can get a3, n equals 3 here, n equals 0 here, and that gives us a3. So we can get a3 is a0 over 3 times 2. Right? We can get then a6, which is, put n equals 3 here, a3 over 6 times 5. a3 is a0, so a3 over 6 times 5, and a3 is a0 over 3 times 2. Okay, so a3, a6. And if we get one more, it would be a9, and that would be a9 would be a0, and what do we have? 6, 5, 3, 2. So then this one would be 9, 8, 6, 5, 3, 2. Okay? So that's the first sequence. That one starts with a 0. Okay? The second sequence will start with a 1. Starting with a 1, here n equals 1, we will get a 4, and that will be a 4 times 3. So starting with a 1, we get a 4, which is a 1 over 4 times 3. And it's the same sort of pattern here, so we go up by 3. So a 7 is a 1 over 7 times 6 times 4 times 3. And a 10 will be a 1 over 10 times 9 times 7 times 6 times 4 times 3. Okay? So now we should be able to write the final solution. So we get y of x. The first series will start with a 0, so we'll have an a 0. And the a 0 has the leading term x to the 0, which is 1. And then we have a3, so plus a3 multiplies x cubed, and it's a0, which we factor out, over 3 times 2. The next term is a6, so that will be x to the 6 over 6 times 5 times 3 times 2. And the last term is x to the 9th over 9 times 8 times 6 times 5 times 3 times 2. And that becomes our first power series. The second power series leads with a1. So a1 times x. And then we have a a4. So that's a4 times x to the 4th. And a4 has a 4 times 3. And then the next one is x to the 7th over 7 times 6 times 4 times 3. And then x to the 10th over 10 times 9 times 7 times 6 times 4 times 3 plus. And then there's drop terms here. So it's just like in the first one, there should be some drop terms. Okay? So the solution of the Airy's equation by power series then gives us two independent power series. One with a free constant a0, the second with a free constant a1, and then these are the two infinite power series.